Hello, General Chemistry students. This is the sixth video in week 11, and we are going to be exploring reaction mechanisms and catalysis. So by the end of this video, you'll be able to describe the types of catalysts, how catalysts affect things like activation energy and reaction rates, and you'll also describe a little bit how biocatalysts such as enzymes, how they function. All right, so let's look at this mechanism. So we have A plus B goes to AB plus B. That's the slow step. That's the rate determining step or rate limiting step. So if the slow step is the first step, then the overall rate is the rate of the rate determining step. Okay, so what I mean by that is this is the overall reaction because B is an intermediate. The first step is rate determining, which is rate times K times A times B2. Notice that there's no intermediate in the rate determining step. And so the overall rate is described here as the rate determining step. All right, so let's talk a little bit about catalysts. So catalysts, what they do is they speed up reactions. They affect the rate of a reaction, and importantly, catalysts are not consumed during the reaction. So they, what they do is they provide an alternative mechanism so that it can lower the activation energy. Remember, lowering that activation energy is the key to speeding up the rate of a reaction. All right, so let's look at this reaction. So this is the formation of ozone the degradation of ozone into O2 gas. Without a catalyst, this mechanism is extremely slow. But if we add a catalyst, like a chlorine atom, this happens pretty fast. All right, so the chlorine atom acts as the catalyst here to degrade ozone O3. And this was first discovered when CFCs were discovered to deplete the ozone layer. And what was happening is it was providing chlorine atoms that would then degrade the ozone layer. Okay, so this is what it looks like. So over the Antarctic, over time, that ozone layer has started to become depleted, and in some spots, really not much ozone at all. And this was discovered because of the use of what's called CFCs, or chlorofluorocarbons. And they were used a lot in things like spray cans and refrigerants. And they were actually really good at what they did, but the problem is when they were released into the atmosphere, they catalyzed the depletion of ozone by producing that chlorine atom that we just showed on the previous slide. All right, so let's talk about catalysts and how they work. So catalysts generally speed up a reaction. There are examples of catalysts that slow down a reaction, but for the most part, they will speed up a reaction. And they do this by lowering the activation energy. Okay, so a catalyst is really going to change the mechanism of a reaction so that the overall activation energy is lower, therefore speeding up the rate. And there are two types of catalysts, or chemical catalysts, that we'll talk about, the heterogeneous catalysts and the homogeneous catalysts. The heterogeneous catalysts are when the reactants are in different phases of each other. And homogeneous catalysts are when they are in the same phase, like in solution. All right, so again, the the catalyzing of O3 to produce O2 gas. Normally, without a catalyst, we have an activation energy right up here, and this reaction is extremely slow because of the very high activation energy. But by the addition of that chlorine atom in the atmosphere, we have changed the mechanism. So remember, we had 2 elementary steps, and because there's 2 elementary steps, that means that there are 2 activation energies. But overall, the energy barrier is lowered. Okay, so we have 2 elementary steps here, each with its own activation energy, but overall a lower activation energy. Therefore, a faster rate. Okay, so let's look at this mechanism. So we're going to look at this overall reaction, or determine the overall reaction. We're going to determine what is the rate determining step, and we're going to determine the rate law, identify the catalyst and intermediates of this following reaction. Okay, so we got a lot to do here. So the first step is fast, the second step is slow. Remember, if there's a fast initial step, that means that we have an intermediate to consider. So we can say that the that QR2 minus is an intermediate, so I'll just cross it out. We can say that the overall reaction is HQ2R2 forms Q2R plus HR. Okay, so why do I say that? So I just crossed out the intermediate. That was Q2R2 minus. We also have something that's not being consumed in the reaction, and that is R minus. So we're going to cross that out because that is the catalyst, all right? So R minus is the catalyst, Q2R2 minus is an intermediate. All right, so now that just leaves us with what's left, and what's left is the overall reaction. So we cross out intermediates, we cross out the catalyst, that's the overall reaction. All right, so now we need to determine what is the rate determining step. All right, the rate determining step is right here because we just defined it as the slow step. So rate is equal to K times Q2R2 minus. Remember, that's the intermediate, so we need to solve for that. So the rate is equal to HQ2R2 times R minus. This is the catalyst. So here, the rate, or the rate law, cannot have the intermediate in it because it's being consumed in the reaction, but it can have a catalyst in the rate law because that doesn't get consumed in the reaction. All right, so let's consider these types of catalysts. So the homogeneous catalysts are the ones that are in the same phase. So we talked about the example of chlorine atom, chlorine gas, destroying the ozone layer, so O3. That's an example of a homogeneous catalyst. A heterogeneous catalyst are when those reactants are in different phases. So example here is the catalytic converter in a car's exhaust system. So the catalytic converter is a solid metal, so you can see ceramic substrate for the catalytic metal, and what's going in are the gases, and it's turning those gases into we'll say better gases. So N2H2CO2 are better gases to come out of the catalytic converter, at least for the atmosphere, than say CO, the hydrocarbon, and NO2. So that's the point of the catalytic converter. An example of the heterogeneous catalysis. All right, so this is what it might look like on the molecular scale. A homogeneous catalyst, they're all in the same phase. And so they really have the ability to react together much more easily than heterogeneous catalysis. Because in heterogeneous catalysis, the catalyst is in a different phase than the reactants. Okay, so your reactants on the right-hand side are in the gas phase, and your catalyst is in the solid phase. So an example of heterogeneous catalysis is catalytic hydrogenation. So ethene comes in, so this is a C2H4. Ethene comes in, hydrogen comes in onto, and it absorbs on this surface. All right, and after it absorbs, it diffuses into the surface. So just on the outside of the surface. Remember, this is a solid phase. The reaction actually happens at the surface. So the higher the surface area, the more reaction you can get to take place. And then after reaction has happened, then there's desorption. All right, so let's give an example of a type of homogeneous catalysis, and that is with enzymes. So enzymes are biological catalysts. What they do is they perform biological reactions, or biologically necessary reactions. A lot of biological reactions tend to be very slow, tend to be not very thermodynamically favorable. What enzymes do is they work just like other catalysts, where they change the mechanism of the reaction, thereby lowering the activation energy of the reaction. All right, so this is how enzymes might work. So you have an enzyme and a substrate. All right, this is the thing you want it to react, and it forms an enzyme-substrate complex. All right, this is your fast initial step. That enzyme-substrate complex reacts to form the enzyme and product. This is the slow step. This is the rate determining step. All right, and so how this works is you have an enzyme and a substrate, and it can work according to this lock and key mechanism. So the substrate can come in to the active site and bind. And the active site is going to be the right shape and have the right intermolecular interaction so that the substrate can come in and bind. And then once you have the enzyme-substrate complex, the binding of that substrate stabilizes a transition state, which then lowers the activation energy of the reaction, making the reaction faster. All right, and so at the end, the enzyme can release products, all right, because the product is no longer binding to the active site because it doesn't have the appropriate shape, it doesn't have the appropriate intermolecular interactions. So the product can go and leave the active site. So here's just an example of one type of enzymatic reaction, and this is the hydrolysis of sucrose. So sucrose is a sugar that you put on your cereal, and it is made up of a glucose molecule and a fructose molecule. And so Sucrase enzyme, what it does is it cleaves the glucose and fructose molecule right here to release two sugar molecules, glucose and fructose. And so sucrose comes into the active site and binds to the sucrose enzyme. And at the active site, it's the right shape, it's the right intermolecular interactions. And what it does is it strains this bond. This is the one it wants to cleave. And so it strains it almost like it's putting it into its transition state. And when it does that, it weakens that bond, making it easier to be cleaved, make it easier to break that bond. So enzymes really have that ability to situate a substrate so that it can weaken those bonds it needs to break and can strengthen those bonds that they want to form. All right, so that's the end of kinetics for it. This is the end. This is the last video in week 11, and it is really the official end of our kinetics unit. Thank you.